A ball is rolled off a 0.5 meter platform at 3 meters per second. How far away does it land? So we have a ball that's here. It's rolled off of a platform with this initial velocity of 3 meters per second this way. And of course, as soon as it's off the platform, it's going to start to fall. And it'll follow a path like this. And it's going to land here. And the question is, how far away does it land? So what is the displacement along the x-axis going this way? So here's how we're going to solve this. We're going to use vertical analysis to determine how long the ball is in the air for. We're then going to multiply that time in the air by 3 meters per second to determine how far forward it goes. So I've told my students, see this subscript x? Everything that's written on your page, it should be immediately clear to whoever's looking at it exactly what that quantity is. That x means that we're referring to the displacement in the x direction. So that's horizontally. We know the actual displacement is the difference from the position from here to here. So it's going to be downward and forward, and it's going to have a magnitude along that hypotenuse. However, we're only looking for how far away from the platform it lands. So that is the displacement along the x-axis direction. There's two ways we can do this. We can put a little x and a little y beside all of our kinematics variables. Or the way I'm going to do this here is I'll put a title, vertical, horizontal, to separate the work. And I'll draw boxes around it just so that it's clear. So we're going to determine how long that ball stays in the air by doing vertical analysis. So I'm just going to write that here. Vertical. And we'll enclose all of our work in a box, so when we look later, we'll realize all of that's vertical. Vertically, as the ball falls from here down, its displacement is negative 0.5 meters. Now again, if I didn't label that vertical, I'd put a little y here so that I know that that means vertical. Our displacement's negative 0.5 meters. Our acceleration is negative 9.8 meters per second squared. Later on, when we study gravity, you'll learn that near the Earth's surface, if you look at the way gravity works in conjunction with Newton's second law, all objects accelerate towards the ground at a rate of 9.8 meters per second squared. That's why this is a negative, because we're assuming here that up is positive and down is negative. And we have an initial velocity. This one's a little surprising to some people. A ball is rolled straight off a platform. Vertically, its initial velocity is 0. If it was rolled forward, not kicked upward or thrown downward, but rolled forward, when it comes off that platform, its initial velocity is all forward. There's nothing up nor down. So the vertical component of its initial velocity is 0. So our initial velocity is 0. That's going to make solving this real easy. Your fundamental displacement equation when acceleration is constant. Displacement is your initial velocity times time plus half acceleration times time squared. Again, all of this is vertical. Our initial velocity is 0, so this will simplify to negative 0.5 is equal to negative 4.9 delta t squared, or delta t squared is 0.5 over 4.9, making delta t equal to the square root of 0.5 over 4.9. That square root covers the entire fraction, so we're going to evaluate the fraction and then take the square root. And when we do that, we're going to get 0.319. So delta t is 0.319 seconds. So to recap so far, we have a ball rolled off of a platform. To determine how much time it spends in the air before it hits the ground, we analyze the problem by looking only at the vertical components of our kinematics variables. The displacement, this thing is falling 0.5 meters. It's accelerating towards the ground because of gravity at 9.8 meters per second squared, and it has an initial velocity of 0. Here's our fundamental equation that deals with displacement when you have constant acceleration. Because our initial velocity was 0, it was simplified, do a little bit of algebra. All of that is to determine time. Now, time is the same both vertically and horizontally. We don't have vertical and horizontal components of time, certainly not when we're doing Newtonian mechanics, which is what we call this classification of physics. So, horizontally, our time, delta t, is the same. It is 0.319. Our velocity is 3 meters per second. So you remember the ball was rolled off at 3 meters per second. Now, that's our initial velocity. However, there's no reason to believe this ball is accelerating forward or backward. So that initial velocity is the constant velocity, is the average velocity, so I'm just calling it the velocity. Our displacement will then simply be the velocity times the amount of time. So it is 3 meters per second forward, that's forward, 3 meters per second forward, multiplied by 0.3, what was that again? 0.319 seconds. And that's going to give us 0.96 meters forward. So this ball is going to land 0.9 meters, almost a full meter, away from that platform if it's rolled off at 3 meters per second. We analyze the motion vertically to determine how much time it spent in the air, and then we use that time in conjunction with its horizontal component of velocity to figure out how far forward it went. Now, a variation on this would be if you were given a ball that was kicked upward or thrown upward. And if that was the case, you'd have to be given this angle here. And in such a case, you would find the vertical component and the horizontal component. So if that was V, this would be Vy and Vx. Vx would be V cos theta, and Vy, well, the magnitude of V cos theta, and Vy would be the magnitude of V sine theta. And then you could use those components, you could use that vertical component to determine the time that this was in the air. Now, you would also have your, this is the y component of your displacement, and it would come out as a negative. When you set up your quadratic, the difference is you have an initial velocity, so you'll have to use the quadratic formula to solve it. I mean, there's no chance you're going to have a factorable quadratic. That's ridiculous. So that'll be a problem you'll run into in grade 12, where you've got an angle of inclination, these components, and you're on a platform. Basically solved the same way, with a minor complication that that's not 0, so few more steps involved. For this year, and so for anyone watching this who's not in my class, it's a introductory physics class. Our projectile motion problems will either be purely horizontal off of a platform, or if you're given an angle of inclination, it's going to be a soccer ball or perhaps a football kicked off the ground, maybe like a golf ball. So it's problems where, and there's another video on this, where you've got this initial velocity, but it's on the ground. And so that ball goes up and down, and we solve those by finding the vertical and horizontal components. Use the vertical component to determine the time in the air, in conjunction with the fact that the y component of your displacement, if it was from ground to ground, is 0. Again, that simplifies the quadratic so that you got a little less to worry about for this year. Good luck. Good luck on your test on Friday, guys.